Hello, everyone. Welcome back to the PSSS seminar. Today we have Dr. Tony Gargano here today. And with that, I will leave it to Dr. Sharp.
All right. Hey, everyone. It's a pleasure to introduce Tony Gargano, who did a PhD student here, working in part with me and others on a wide range of stable isotope topics, and has a couple of fantastic papers about chlorine isotopes in the moon and other planets, and has kind of redefined the way we think about volatile elements in certainly in appetites, and has continued to do some really cutting edge and innovative science, which maybe sometimes makes things difficult because it's not always easy to get something published that is maybe a little bit outside the mainstream. And this is something he's talking about today, just some fantastic work on the lunar regolith, and just fits in line with Tony's creativity and hard work and excellent quality of research that he's done throughout his career. So take it away.
All right, well, thanks, Zach. All right, so I'll be looking at the screen a bit here so I can point out things to people online. We'll have plenty of time for questions, so feel free to interrupt whenever. I'll full screen this side too, so I'll go over here and see it. Is that good enough for everyone here?
Yeah, I think that's good.
All right, great. All right, so the laser pointer is working. Perfect, great. Okay, so thanks for having me, everyone. My name is Tony Gargano. I'm a postdoc at the LPI, work with Justin Simon at the moment. This is a project we've been done now for almost a year, but it's been difficult getting it through review, and hopefully it'll be out soon. But today we'll be going through this talk and answering the question of whether or not oxygen isotopes can tell us how much and what type of exogenous material has been delivered to the Earth-Moon system over geologic time. And hopefully after this talk today, you'll think yes, but appreciating the many nuanced difficulties related to incorporating what we know about regolith and interpreting this long-term impactor flux record. So with that said, let's get into it. And I'm working on my logical train of thought here these days. So we're going to build on some concepts, building up what regolith is, what it represents, and building up the story about how the oxygen isotope comps of regolith tell us about ancient impactor fluxes. So we'll begin talking about how ancient impactor fluxes cannot be determined on Earth. We'll follow that by talking about how what regolith is and how it records this time-integrated impactor flux record to the Earth-Moon system. Then we'll get into some of the complicated, nuanced details about how chemical and isotopic proxies can be influenced by many competing geochemical processes. And then lastly, we'll get into the meat and potatoes of this talk and the data about how the triple oxygen isotopes can be used to deconvolve these multivariate processes of impact processing and inform this ancient impactor flux. So that said, we'll go through each of these topics in order and kind of build up our concepts of what this material is and what we can use it for. So let's begin on some common ground here. And this is commonly thought of in terms of impactor processes looking at siderophile elements and metals. This is a plot showing the depletion in Earth's mantle relative to CI chondrites of elements of increasing siderophile behavior. This is showing elements with very high metal silicate partition coefficients. And when a body differentiates, its silicate reservoir is effectively quantitatively depleted of these elements. And this behavior means that if you add impactor material to a differentiated body, you can very easily clearly see this enrichment in highly siderophile element contents. But the issue is that when we apply these systematics to a really complicated material like regolith, these elements are not retained quantitatively during multiple events of melting and crystallization. And really what this reflects is the fact that these elements have very different geochemical affinities and lithophile elements. So now we're going to start going through this logical progression of how the story develops and why we're looking at regolith for this problem. So we'll begin talking about how ancient impactor fluxes cannot be determined on Earth. And this argument is really clearly seen in terms of the age of oceanic lithosphere across the Earth, where we can see that the more or less the oldest terrain at spreading centers is around 200 million years old. So really these ancient impactor fluxes are things that are around 4.5 to 4 billion years old, and not much terrain on Earth is preserved or even present that's that old. So if you go to the terrestrial land surface, you can see more of these ancient impact terrain. This is a distribution showing you the size and ages of some of these impact craters across the Earth's surface. And the key thing I want to point out to you here is that although we have many of these impact craters present, much of them are not very old and ancient. Only a handful of these are Precambrian in age, and they're not distributed across the planet. And the same idea can be seen in terms of the age distribution of the impact ejecta and these impact craters too, where our record of this is very much biased to the modern impactor flux. We don't really have samples that record this 4.5 to 4 billion year old period of impactor flux history to the Earth. So we're left to go to the moon. But that's fine because the moon has a wealth of pristine samples we can use to understand this process better. So now this is why we're going to regolith for this story, and we're going to begin really simple here and explain what regolith is and what it represents on a broader, the broader geology of the moon. So in the most simple sense, regolith is a thin meter-scale surface deposit of fine-grained material on the moon. I love this picture on the left here because it shows the textural qualities of regolith very well. It is effectively a powder. It is largely a fine-grained material. The mean grain size is usually around 70 to 100 microns. But there's both this really fine fraction powdery material, but also macroscopic particles present there. And those macroscopic products represent the in situ protoliths that are broken down to form that powdery material. Now, placing this in context for the stratigraphy of the lunar crust here, I want to point out that this is an idealized idea of what we think about the lunar crust. The regolith is this rather thin meter scale deposit on this tens of kilometer scale stratigraphy. But what I want to point out to you is the fact that this regolith is a thin, small mass reservoir, but it is beneath what is effectively an extensively impacted terrain in this large scale ejecta and structurally disturbed crust. And we can refer to this as the mega regolith. It is basically the extensively processed crustal terrains that are likely representing that earliest period of impact bombardment, and the regolith is forming on top of it. And what this means is that the regolith is constantly sampling this ancient terrain that we can't really see to this day. All right, so I've already kind of explained about how regolith is this mixture of both fine-grained and macroscopic particles. And a critical thing to understand here is that all the bulk regolith we sample today from the Apollo collection was all sieved to remove its 1 to 2 and 2 to 4 millimeter size fraction of particles present there. So what we sample now is the less than 1 millimeter size fraction of that regolith. But for all we know about this material, we generally think that this macroscopic material represents the in situ protoliths that are broken down to form the fine fraction material present there. And what you can see here, and this changes depending upon what Apollo mission site you're at, but we have a large distribution of particle types in this material. There's no single age for this material because you have this collection of different materials present here, ranging from primary igneous rock fragments to breccias, impact glasses, and other weird things present there too. So it's a mixture of a lot of things. And what I want to convey here is the fact that the regolith forms from the process of impact processing. And what this idea of impact processing does is that it creates a continuum of impactor target mixtures with some small degree of vaporization that occurs during the impact process itself. So this is an idealized kind of cross section of how we think about the impact process. And really what I'm trying to convey here is that during any one impact process, we're forming a continuum of mixtures, and some of those mixtures are fractionated by the process of vaporization or physical fractionation of the different material. All right, so now building up our concepts here, this is where things start to get a little complicated. Before we move on, I want to discuss a couple things first, and that's largely related to how does the impactor flux change with time, and how old is the regolith? So we'll go through this one step at a time here. So one thing we can generally agree upon is the fact that we know that the impactor flux was likely highest at the beginning of the solar system and decreased exponentially with time. You can understand this in many different ways, and this will be debated a lot, but we can generally agree that the impact flux was highest early and declined exponentially with time, and at the minimum now. You can model this in many different ways. This is a model looking at the highly acidophile element content of the moon. So again, looking at that metal-like proxy for the impactor mass added to the moon. And really what I want to convey here really is that if we look at this plot of impactor mass addition over time, if we look at 4.5 to 4 billion years, we've dropped our impactor mass addition by around 2 orders of magnitude. So most impactor flux occurs early, and that means most of the record we have is sampling that period of early bombardment. Now back to this question of how old is the regolith, and I already kind of touched on this too. Regolith doesn't have a defined age. It is sampling the material that is beneath it, and it's always mixing it up. And what we're really curious about here is trying to understand what is the time period the regolith represents. And there's a concept that our group is really talking about a lot these days in terms of the idea of the lunar dark age, where if you look at the ages of crustal highlands rocks, we have a pretty confident age of around 4.35. But if you look at the argon ages of regolith breccias here, oldest we have is around 3.8. So we have a long time period of missing history of the moon during its most tumultuous impact process time period. I think regolith is probably our best bet for sampling some of that ancient impactor flux. So kind of going deeper into this idea of how old is the regolith, this is understood in terms of kind of a stochastic modeling of a size distribution of impactors and how often it hits something and how deep it excavates, more or less. We'll build on this concept going forward. This is kind of a complicated plot here, but long story short here, you got to understand is the fact that materials at the uppermost surface are extensively mixed, and that mixing interval decreases exponentially with depth. So I'll key in on this figure C here, where basically the uppermost part is homogeneous by efficient mixing, and that mixing is more or less efficient with depth, where things at depth are largely undisturbed. Now, I think it's best to understand regolith in terms of the idea that it's a dynamic steady state reservoir. It is always being destroyed and accreted. So in this kind of concept here, in the idea of how the impactor flux declines with time here, effectively, I think we can think about this in terms of the accumulation of regolith becomes more efficient as the impactor flux goes down. This is a great plot from Dave McKay kind of describing these systematics. What is being shown here is the hypothetical height of a regolith reservoir, beginning from time zero with lunar formation going to the modern. And more or less what you can see here is the fact that at some time period where the impactor flux declines enough, the regolith stops being destroyed and starts accumulating. So whether you want to say that regolith is sampling this acute time period of when it starts to accumulate, or it's sampling older things, long story short here is that this thin scale, meter scale reservoir is sampling this kind of decay of the impactor flux, and it's been accumulating ever since. And again, kind of still touching on this idea of how old the regolith is, if we put in context the idea of these macroscopic particles being the in situ protoliths being broken down to form that fine fraction material, there's no single age here. We know that the age distribution of this material is wide-ranging, meaning that the age distribution here is wide-ranging as well. And this is borne out with the argon-argon data as well. This is a plot from Nicole Zellner showing the argon-argon ages of impact glasses and regolith. And really the simple story I'm trying to convey here is the fact that the materials, the macroscopic materials that make up regolith have a wide age distribution. This tells us that regolith is not a single age. You're always sampling some of this really old stuff present there. You're sampling modern stuff as well, but it's a mixture of all these things. And lastly, we can think about this as well in terms of cosmic ray exposure ages. These ages reflect the abundance of particular isotopes that are very sensitive to neutron capture reactions. And they tell us when a material was last exposed to these energetic particles. The plot on the right is showing you a variety of ages for these materials. And the plot on the left here is some recent work out of UChicago from Justin Hu, where he's using gadolinium isotopes, one of these isotopes that are very sensitive to neutron capture, where he's performing a Monte Carlo simulation looking at how often and how deep does the regolith get overturned. And what's being shown here is that on the timescale of every couple 100 million years, the regolith is being overturned by large-scale impactors to a meter-scale depth. And if we combine these two understandings, this kind of builds our picture here, where this combination of both shallow and deep mixing from different size impactors results in a relatively well-mixed, time-integrated reservoir. And really what this represents is larger impactors relative to micrometeorites present here. But both these things are operating together. So to kind of conclude this idea of how old the regolith is, the way I'm thinking about this is that there's no singular age and there's no simple linear progression of how old the regolith is. It's been continually processed since it began to accumulate, and it is recording the time-integrated impactor flux. And since most of this flux occurs early, the impactor mass fraction is likely weighted towards that earliest period of bombardment. Again, we're sampling that mega regolith continuously as this regolith is forming over time. And to build on this concept of there's no simple linear progression, I'm going to start developing the idea of how does this regolith change as it gets impact processed. This is the plot showing you mean grain size on the y-axis relative to regolith depth at different Apollo mission sites. As most of us know, Apollo 16 is where we have an abundance of highlands and orthocytic lithologies. We have a deep primordial crust. And as we expect there, the regolith there is the deepest and the finest grain size. This tells us that that material has been reworked for a relatively longer period of time. But the concept that's really important to understand here is this idea of the formation of secondary and tertiary lithologies as the regolith is being evolved. This is showing a modal distribution of different particle types in an Apollo 17 regolith dominated by marl basalt materials. And what I want to key you in on here is if we look at particles above 1,000 microns, we're largely at our primary rock fragments, our basalt fragments. But with decreasing grain size, we're making new particles. I want to key you in on the impact glasses and the agglutinates here. These are really important. And really what I'm trying to show is that we are forming new materials from the breakdown of old materials. So I think these agglutinates are best thought to represent the material being recycled over time as the regolith is continuously being reworked. Here's a picture of one of these agglutinates. An agglutinate is a highly classic vesicular impact glass. This image on the left here is showing us one. This was collected from the Angsa core. And what you can see here is that this particle has a variety of class within it, has a variety of glass chemistries. It is full of vesicles. And it's kind of showing us this process of making this weird material from these impact processes. So if we look at this agglutinate particle present here, what you can see is that these vesicles represent gas being lost from the material. Whether that gas be hydrogen or vaporized silicates, it doesn't really matter. This material represents we have a system where we're losing material as the regolith is being overturned and reworked. And if we look at the chemistry of agglutinates relative to bulk regolith, and this is a lot of work done by people at UNM, Jim Pike and Steve Simon, for example. And what we're seeing on the plots here are the chemistry of the agglutinates relative to different bulk regolith fractions. The line at 1 here will indicate when an agglutinate is the same chemistry of the bulk regolith, and the differences here relate to either enrichments or depletions in that material. And although there's a lot of variety present here, in general, we can see a depletion in iron, magnesium, manganese, and enrichment in aluminum, calcium, and alkalis as well. And what I want to convey with this is that this suggests that regolith evolution is not simply loss-driven. Both loss and gain are occurring simultaneously during the recycling of that fine fraction material into the agglutinates, and ultimately, the cycle continues. All right, so now we've kind of established what regolith is, the kind of processes going on that we need to be sensitive towards. And now I'm going to go into how these chemical and isotopic proxies can be obscured by other processes and start to build up this idea of kind of constraining a mass balance of what is the mass loss and mass gain as the regolith is evolving over time. And ideally, your proxy that is the least complicated is insensitive to other processes. This is a great figure showing kind of this grab bag of processes that we kind of lump into the idea of impact processing and space weathering. And I've circled 2 here, cosmic ray and solar wind implantation. These 2 processes reflect energetic particle reactions that relate to forming weird isotopes. More or less, the sensitivity of these reactions relate to the neutron cross-section of the element present there. We point out gadolinium here. I spoke of earlier how gadolinium is the proxy used for the cosmic exposure age and this neutron cross-section reaction. But in addition to this, the highly sterile elements are also high up here as well. And what this means is that although these elements are commonly used to look at impact irradiation, we have an additional complication in their use in terms of relating it to regolith specifically. This is some old rhenium osmium data out of UCLA. Never got published past an LPSC abstract here. But what this shows here is that if we look at the rhenium osmium age of regolith here, these things fall off the isochron present here. And this relates to neutron capture processes. So this additional complication makes these elements hard to use for the story present here. At the other end of this extreme, oxygen is present. And what this means is that we have a more simple proxy here of looking at mass loss and mass gain because we're not so sensitive to those exposure effects. So we kind of just covered some complications related to gain, relating to proxies that complicate the story here. But now we're going to talk about the process of loss. In this idea, your ideal proxy shouldn't be fractionated by different loss processes. And in this case specifically, I want to key in on the idea of vaporization and condensation, as well as physical fractionation of materials that don't mix very well. So we already kind of spoke of this earlier about how during any given impact event, we have a mixture of impact or target materials, as well as some degree of fractionation relating to vaporization. If we look at a plot of the condensation temperatures of the HSCs here, what I point out here is that although the most refractory HSCs, rhenium osmium, are condensed at very high temperatures, really we have several hundred degrees separation between the most refractory HSCs, the more volatile HSCs, and that of iron present here. And this is to say that in any event where we have vaporization condensation, we have the possibility of fractionating the inner elements of the HSCs. And this complicates the use of them for identifying the impact present there. In addition, the physical mixing of this material is also a bit not as clean as we'd expect. The plot on the right is showing a piece of ejecta where we have an iron meteorite impactor mixing with a silicate material. And what you can see here is that we have an abundance of immiscibility textures present here, showing us that our impactor material is not quantitatively mixing into the lithophile reservoir in that ejecta. The figure on the left here is showing you this idea of a physical fractionation of an immiscible phase present here. And what I'm trying to convey here is that these two factors means that we are adding additional complications when we're using siderophile elements that are in a lithophile reservoir for identifying and quantifying how much impactor is present there. So now we've covered kind of the general background. I think we need to discuss this story. And now we're going to get into the meat and potatoes here and discuss how the oxygen isotopes can be used to deconvolve these processes that inform the ancient impactor flux. And we're going to go through this in step by step here. We're going to begin by talking about how does impactor addition look like in isolation. So just that singular process. And then we'll add the complication of how we can deconvolve the silicate evaporation from that addition. So the plot on the right here is a triple oxygen isotope plot of the solar system. We're going to break this down step by step so you get what's going on here. This is showing us the 1816 oxygen and the 1716 oxygen isotope ratios of these materials across the solar system. I want to key you in on this small green oval for the Earth and Moon. The Earth and Moon have very similar oxygen isotope compositions. And these materials fall in a 0.528 slope line that defines a high temperature equilibrium in that phase. So every material from the moon that is a primary igneous rock that does not have obvious impactor contamination will fall on a 528 slope at around that composition. And now I want you to conceptualize mixing with impactors that fall at different points on this curve. So I've removed some fields here, but I want you to assume mixing of different things, whether it be a CO, CV, CM, or an R chondrite with that moon-like material. And what we're going to look at is this term big delta O17. And I've pointed out one right here on the top here. This big delta O17 more or less shows us the deviation in the y-axis here, but more specifically, the deviation in the slope. And we're going to play a game here to get an idea of what this mixing space looks like here. So we're going to conceptualize mixing our pristine moon material with arbitrary thing red, arbitrary thing green. So in the idea of mixing with red here in this case, if we take our pristine moon material and mix it with red, we're going to decrease the delta O18 value and the big delta O17 value. And in the case of arbitrary green, the opposite is true. We'll be increasing the delta O18 and increasing the big delta O17 values. So now I'm going to change this space now to, instead of plotting what we call the little delta 17, we'll plot that big delta 17, that deviation in y-axis space. So this kind of looks like this plot on the left here, and this plot will be used again here. So we'll break it down step by step here. This plot is showing us the mixing array of different impactor types. The bulk moon origin is what we call the pristine bulk moon, is what we think the moon is without any impactor contamination. The horizontal gray bar is the plus or minus deviation of that pristine bulk moon value, what we think that plus or minus is. And these mixing arrays go to different impactors and the average within that group. So I want you to key in on first on the plot on the right here and look at the mixing array between the ordinary chondrites, H, L, and LL, as well as the R chondrites here. So I want you to imagine mixing with bulk moon going up to those materials. And now look at the plot on the left here. We can see this really clearly now, where for mixing with HLs or LLs, we're going to increasing big delta O17 values with very little change in delta O18. But if you look at R in this case, since R is so much higher, we need comparatively smaller impactor mass additions to increase our big delta O17 value. And likewise, if we're mixing with other C chondrites, we get a wide array of solutions. And this is effectively an infinite mixing array depending upon what you want to do. But this gets simpler as we go on because it's less complicated than this seems to on the onset. And I think that's good for this. Okay. All right, so now we're going to get a little more complicated now and talk about this process of silicate evaporation and how can this be deconvolved from the impactor addition. What these curves are showing us are silicate evaporation lines at different triple oxygen slopes. What you're seeing here is a change in the delta O18 value to the right with increasing evaporation and a change in the big delta O17 value as well due to evaporation. And what I want to key you in on here is that with a decreasing slope in triple O space, we're causing a relatively large deviation in big delta O17 per deviation in delta O18. The slope for this probably varies a little bit, but it's not very relevant to the grand scheme of things. What's important here is the fact that when this slope is not 528, we cause changes in big delta O17 with changes in delta O18, which we see in the regolith. That's what matters here. If we plot how this data looks in terms of the mass loss and how much it changes, this is all the available literature data set present here. These series marks are 5% loss markers. I pointed out two here being the 10% and 20% markers present here. And what you can see here is that if you want to cause a minus 0.02 deviation in big delta O17, you must reconcile above a 2 per mil change of delta O18. So these two things play together in terms of how we can constrain our mass balance of how much is lost, how much is gained. All right, so now we're combined all these systematics into our master plot here. This is very busy, so we'll break this down one step at a time here. This is the same plot we showed earlier, where we have our pristine moon being this black origin, this gray bar being the plus or minus what we call the pristine bulk moon. Since plagioclase has a rather high delta 18 value, if a material is more plagioclase rich, it'll be more delta 18 rich with no change in big delta 17. But now let's think about first in terms of the impactor addition. We've retained our two R chondrites going up in the green here. We have going to CI chondrites to the right here in purple, and we have a mixing array that represents the entire field for CM chondrites and ureilites present here. So I've incorporated the minimum and maximum across both these groups, and that's what you're seeing here. Each one of these tick marks is a 1% incremental addition, so 1%, 2%, 3%, etc. This red field is going to be to ureilites, so that includes the minimum and maximum of the full field, and likewise for the blue, that will be for CM chondrites. So now I want you to imagine that we have our material representing either a 1% or 2% impactor contamination. That can be seen by connecting these lines for the 1% isopleth or 2% isopleth for these fields. And that mixture then becomes vaporized. So we move our origin of evaporation to that mixing line for the most part. So next up, what I'm going to do is connect these isopleths for the 2% impactor contamination mixture. And we'll see this field that forms from adding impactors and vaporizing the mixture.
Directions, can you point that out on the figure, please?
The vaporizing directions to the right here. So similarly, we're increasing delta 18 values and decreasing our big delta 17 values, albeit slightly. Yes. And this range in purple is showing us that range we see in the real data sets. All right, so again, complicated plot here, but the same story is present here. What I've done is I've connected the 2% isopleths for both the ureilites and the CM chondrites. The red field is for the ureilites, the blue field is for the CM chondrites. And these slope lines indicate that vaporization along that different slope at that mixture point. So what we're going to see here is that this compositional space reflects the combination of these two vectors, the addition of impactors and the evaporation of the mixture. That's what it represents. Anything in this field represents that material. All right, so let's get into the sample suite now, and then we'll get into the data finally. So in this work, we sampled a variety of regoliths from Apollo 12, 16, and 17. This is bulk regolith across a range of maturities. We also requested the macroscopic particles, that 1 to 2 and 2 to 4 millimeter size fraction material, to represent the in situ protoliths from those bulk regoliths. And we also measured some impact melt coats. This is showing one on the right here. These impact melts are ubiquitous on the fans that we love and dear. And we'll look at how all these materials look like in space and how it informs our ancient impactor flux. And this is a map of the moon showing us how we have a pretty good distribution of different regolith types present here. All right, so I'm going to begin with just the low end of the big delta 17 side of this plot here. And here we're plotting our bulk regolith as well as the particles separated from that bulk regolith. And our same systematics are applied here. We have our impactor mixing lines faded out. And let's go through this step by step here. So here we have our bulk regolith samples in these black circles. The maturity of that regolith is defined by its series marker present there. We have regolith breccias, agglutinates. We have igneous rock plagioclase present here as well, and a couple fans as well present here. And there's several significant things to take from this plot. So all the regolith, independent of the location it was collected or its maturity, falls in the same slope. If we look at the macroscopic particles from that bulk regolith, the agglutinates and regolith breccias, they're indistinguishable from that bulk regolith material as well. And all the regolith tends towards these low big delta 17 values. And the way we're interpreting this is that these data reflect a ubiquitous presence of evaporated and impactor contaminated material in the regolith across the Apollo mission sites. And based purely upon oxygen, we can constrain a minimum impactor fraction of around 1% present here. A key thing to get here is that the origin for this best fit does not intersect the bulk moon. What this means is that this trend line cannot be entirely explained just by vaporization of the mixture. We have to add things to decrease our y-axis coordinate to begin the slope line present here. And this is why we have to have at least 1% of mixing of either CMs or ureilites. We can't distinguish the two. As you can see, these fields more or less overlap. Yes, Steve.
Do you have the presence of evaporated material, evaporated and recondensed?
Yes, effectively. That's an important part about this is better understanding what is the exact series of operations that tends towards this. This is not a singular event. This is tens of thousands of events that we're sampling to this day.
You're assuming complete evaporation and complete recondensation without any fractionation.
We must have some mass loss, but the mass balance more or less constrains us to less than 5%. It's a rather small mass fraction loss by evaporation. And that's constrained by the fact that the evaporation causes large changes in delta O18 values that we don't see. We only see about a 1 per mil increase from the pristine bulk moon for these materials. So we can't justify a lot of evaporation from the material. All right, so now we're going to go to the other side of this diagram, looking at things with high big delta O17 values. And in this, we're plotting those impact melt coats, as well as regolith glasses I separated from the same bulk regoliths. These regolith glasses were agnostic. These likely include impact, volcanic, and otherwise. And what we're seeing here is that these impact melt coats and a couple of these regolith glasses are sampling a very distinct impactor type. And it must be an R chondrite, despite how weird that sounds. This material is clearly subordinate. It is not very abundant. It is not sampled in the bulk regolith. It is something different. In terms of it having to be an R chondrite, earlier we talked about how ordinary chondrites and R chondrites go to the similar mixing space. Since ordinary chondrites are closer to the moon's composition, it means we need more impactor mass fraction to cause this deviation. And if we treat it as an ordinary chondrite, we have around a 3 to 4 times excess in iridium contents. So the R chondrite helps us here, and it makes sense in terms of both the iridium contents and the oxygen isotope values. And some of these materials too have recently been measured for nucleosynthetic isotopes, and they're demonstrably non-carbonaceous, which works with the idea of it being an R chondrite. So everything works out pretty well here. All right, so what does this all mean? Putting it in context here. So we're interpreting the regolith record to reflect the long-term integrated flux, largely being CM chondrites and/or ureilites. Again, we can't distinguish between these two things based purely upon oxygen. There's good arguments to be made in terms of nickel-iridium ratios, in terms of how ureilites cannot dominate the impactor mass fraction. But there's too much iridium in the regolith to just be that from that 1% CM chondrite. So there's something more there, but we can't resolve it. And if that excess metals from metallic impactors, we can't resolve it with oxygen in the first place either. So that's the best we can say. Ordinary and R chondrites are required for the IMCs, those impact melt coats, but they're far subordinate, and they can't be extensively mixed into the regolith at the Apollo 16 site. So a concept I haven't explored yet, and it's because I think it's a bit of a confusing one in terms of this story, is this concept of solar wind implantation and regolith maturity. So this plot on the right here is showing us the metric of isobes over FeO. This is what maturity represents. It reflects the abundance of nanophase iron. And whether we plot carbon, hydrogen, or neon, it's the same story here. Materials with more nanophase iron, more mature, have more solar wind implanted gases. In this case, carbon is solar wind implanted. If we're saying that CM chondrites and ureilites reflect the largest impactor mass addition to the moon's regolith, the carbon content does not allow that. This means that the highly volatile element contents of these impactors cannot be retained in the regolith we sampled today. This means either the highly volatile element contents are no longer present, they've been lost as the regolith has been overturned with time, or they were transferred to the cold traps immediately. So this is telling us that we're sampling a long-term event where some of the chemical abundances aren't there anymore. In this case, carbon's been lost over time as the regolith's been overworked, even though both of our impactors we see would contain a lot of carbon. So now I want to put this all in context for what it means for the moon. The motivation for this story was to look at both the Earth and the moon because they share impactor fluxes. But in terms of taking the story and trying to do the calculation for how much, say, water we bring to the moon from this process, we need to consider the size of that impactor contaminated reservoir. So let's go back to our kind of cross-sectional idea of how thick the moon's impacted material looks like. And really what I want to convey here is that the regolith is a very thin deposit, and it can't be the only reservoir of impactor material because there's way more HSCs in the moon than can be explained by just this meter scale deposit. And what I'm thinking is that the mega regolith, this kind of several kilometer scale deposit of primordial debris during the earliest period of bombardment, I think this material best represents what is the long-term impactor flux. And the regolith is simply continually sampling this over time because it is overlaying the mega regolith. So as we go forward here, we're going to place some minimum and maximum in members by assuming either this impactor contaminated reservoir is thin meter scale or very thick 10 kilometer scale mega regolith. And we'll play some games about how much water can we possibly bring to the moon from this process, and is it significant or not? And then do the same game for the Earth as well. So this plot on the right is showing this kind of systematic here. This is a bit of a complicated plot. We'll show this step by step here. So what we're saying is that we can resolve a 1% CM chondrite-like fraction in the material. We can either treat it as a 5-meter thick regolith at the low end here, or a 10-kilometer thick mega regolith on the high end here. This teal bar is showing us the impactor-derived water mass delivered by CM chondrites of a 1% mass fraction, and the orange is showing us a 10% mass fraction. Just the hypothetical of let's turn the knobs to the extreme. How much water do we bring? To key in on two horizontal lines that matters. This lowest blue horizontal line is what is estimated to be the entire inventory of solar wind-derived water across the entire moon surface and lunar cold traps. And what we see is that our minimum estimate, what we can see already, our 1% mass fraction of a thin regolith reservoir, we're already doubling how much water is present in the lunar cold traps in this process. So that's significant. Now let's turn the knob to the extreme now. Let's say that reservoir is much thicker than we think and has a higher impactor mass fraction present there. We can assume that present to be here. If we look at the one ocean mass line up here, we can see we're barely moving the needle here. So in terms of what we can resolve, even with extreme parameters here, we're not really going to resolve a lot of water being delivered from these impactors. And now the cool part about this is that we can now convey this to the Earth as well. And the general thinking is that because of the Earth is a more massive body, it has a larger gravitational well and it has a larger impactor flux. In general, this is thought to be around 20 to 1, where the Earth gets 20 times the impactor flux to the moon. So we can apply these same systematics of let's do our minimum, maximum end members, and then do that 20 times to the Earth and see how much water can be delivered to the Earth from this process too.
Tony, that 20 times is not the area, it is per area. It's actually a flux.
Yes.
20 times that.
Yes, but it's not agreed upon. These numbers are largely based upon the HSC contents of the bodies, but there's a lot of assumptions built into that. And
it's hard to believe that the gravitational effect is so large.
Yeah, it's not agreed upon extensively to my understanding. But this is part of the story is that insofar as to this day, we only think about this with metals, not with lithophile elements. So this is kind of the first step we can go in terms of relating these two quantities together and seeing if they agree or disagree. All right, so we're going to play the same game for the Earth here, where we have our minimum and maximum impactor material, either at the what we see of 1% or 10%. And the same story applies here. If we look at the one ocean mass line here, horizontal, we're still at a fraction of an ocean for the Earth. Bulk Earth contains around 2 to 8 ocean mass equivalents of water. And what this means is that we cannot reconcile that late addition is a significant part of Earth's water inventory. It just simply cannot be satisfied. If you try to satisfy Earth's ocean water from this process, you start to cause problems with the oxygen isotope value of both the Earth and the moon, which degenerates ultimately. So what we're seeing here is that we really can't justify late addition being a significant source of volatiles to Earth. And to finish up here and kind of put it all in the context here, this record we're seeing that we're interpreting to be the late, or rather the time integrated impactor flux record, we can compare it to the modern record to see, is it different? If it is different, why is it different? And this is a really interesting idea and one that's a bit hard to know confidently because our record is inherently kind of stochastic and not really representative to what it was 4.5 billion years ago. But this is a great overview from Brandy Korotev showing the distribution of different meteorite types present in the collections. And the main thing I want to point out to you here is that our weird rock types we're seeing are the regoliths, the CM chondrites, and the R chondrites. These things are not really abundant. They're rather rare. If we look at the total chondrites here present in this box, we can see of that 93.5%, 90% of them are ordinary chondrites. This is why they're called ordinary. They're the most abundant common one we see. Of that 10% remaining, only 1% of that are R chondrites. In the case of CM chondrites, we can play the game further, where within the grouping of the carbonaceous chondrites, only 5% of that is CM chondrites. And then likewise for urayolites being shown here down to the A chondrites here. These materials are not very abundant in the modern collections. And we can play games about trying to compare micrometeorite records to macroscopic impactors. But the reality is that we don't really know what that ancient record looks like. And we know that our modern record is not representative of what it was in the past either. So this is a really intriguing concept that I'm dubious to develop further. But I'm excited to hear other people's thoughts on it and what this means in the grand scheme of things. And I think that's all I had to cover today. So thanks everyone for your time and listening. And I welcome any questions and critiques. Carl.
I didn't put everything in your talk, sadly, but so there are a couple of things. First of all, I maybe I missed it, but there's actually, there's a really wide range of urialite oxygen isotope values. It's a big array.
Mhm.
And to some degree, that's true for CMs as well.
Correct.
I think the urialites even more so, but,
Mhm.
And then the follow-up question is, have you looked at chromium isotopes? Because CMs and urialites are plotted in totally different places on the diagram. So,
And it's a great idea. I mean, this was started because no one's tried this yet. There was very little data for regolith for oxygen isotopes. And this was an idea started off the Ames mission of how can we begin to understand this process?
Yeah.
And I think the idea of including other proxies is brilliant and great. This is kind of our first step here, and we're trying to get the first step done.
sure.
So I'd be excited to extend it to that.
Interestingly, there are, I don't want to take up too much time here, but interestingly, there are a lot of ungrouped achondrites that plot in the field with the urialites, but they're at minus 1 cap delta, big cap, the terminology,
Yeah.
-1. They cluster.
Yeah.
Sort of at the high end.
Mhm.
I don't know if it has any significance, but you see it over and over again.
It does actually, and this is a point that I've kind of not explored in depth in this trying to get the paper published. But what Carl is saying is that basically the fields of other achondrites kind of fall close to urialites, and that's really valid. And that's part of my story here too, is that we're saying they're urialites, but really what we're saying is that they look like urialites, and a lot of achondrites look like urialites.
Yeah.
It's hard to make the argument of here's the ambiguous array of achondrites, but that's kind of real. And one thing I didn't explore here is, depending upon how you interpret this record, it changes its significance. In terms of the earliest bombardment history, this is more of a question of what is the accretionary feedstock of bodies during near the end of their accretionary periods. If it's a very modern record, that's a very different question of what is leftover crumb is present. So I think the idea of achondrites is great. It makes this story simpler, actually. The issue is that you can't really get a confident value. The urialites are a mess here because they have wide ranges of oxygen isotope values, iridium contents, and the mass balance for that gets really messy. But based on oxygen, we can't resolve them. So the story remains the same. And to clarify your point about the diversity here, that's what this is present here.
Okay.
So the average would fall between these lines more or less.
Yeah.
And this matters. It's just not resolvable with what we can see. So yeah.
Did you superimpose that field with your actual measure data?
I have not, and it's because this field is closer to 1%, and it gets really busy when you start overlaying things like that. So it's just to illustrate how that field
But
will look.
where would your samples plot in this figure? In the pink or in the blue?
Closer to the pink, I would say, just because the urialites, you can get to a smaller change in the delta, big of a 17 value from it. It's closer to 1% isoflux. You can't really resolve them.
Like I know you had mentioned like potentially other proxies and stuff, and Carl just said like chromium isotopes, and so like there's the isotopes. Are you also looking potentially at like trace elements in terms of like nickel cobalt ratios, or like just trying to see maybe if there's like a way to kind of just differentiate between say the R and the urialite and this
Yeah, I mean, so the use of metals for this is a bit of a mess. I didn't talk about this, but for a long time it was suspected that say the nickel contents of regolith were always bad and contaminated from the sieves. James Bay has shown that that's not the case. You can measure the HSC blank when you sieve material in the same sieves. It's hard to know. There's a ubiquitous prevalence of metal in the regolith, and it's doesn't appear to be kind of a consistent origin behind it. So I think each proxy needs to consider the nuances that relate to how it changes. For oxygen, it's always behaving the same way. It's always in a silicate. It is not changing its geochemical affinity. It's a simple story of you're adding and removing material. You're not separating it like the HSCs can be. So I very much welcome other proxies, but they're sampling different processes because they behave differently. So I think that's what's hard about it is understanding what are the processes that explain why the HSCs and oxygen don't agree. And in the case, I didn't talk about this, but in the case of the impact melt codes, what's interesting about these materials is that the HSCs do not look like ordinary or chondrites. So it's telling us the exact scenario of in these really beat up mixtures, these easy systematics don't really play out to be true. So yeah.
Where are the HSCs?
Anything online yet?
So far, nothing online. Of course, if anyone has any questions online, feel free to either put it in the chat or
Raise the volume. I
think we might be muted. So if someone has a question, well, we're not muted mic wise, but
Sorry, everyone.
all right. Let's see. Let's see. It looks like
If I can say something, hi, this is Karen.
there we go.
There we go.
All right, let me turn you up a little more.
We can just now hear you.
All right, you're good now.
Oh, okay. I totally agree with what Carl has mentioned about adding the achondrites, because there are so more different kind of unclassified achondrites that are taking up a fairly big area in between, like on a 3-isotope plot where you plotted them between the urealites and then the Earth Moon. So it would be just interesting to see how that would fit in with your mixing lines.
Yeah, so what Karen is saying is similar to Carl, is where the groups of these other ungrouped achondrites, it's pretty expansive, falling in that field of materials that are close to delta 18 with the moon, but with low because 17 values. I think this is a great idea, and initially when I was writing this up, I was going to develop it more. The issue is that we don't really know what to compare. Trying to make the story work for both metals and silicates, it's hard to relate those two things together. And it becomes even more of a mess in terms of trying to make that for ungrouped achondrites. So I love the idea.
I also think that because you have all the different chondrites in there, and then you have the urealites as the only primitive, and then you're kind of leaving out a significant portion of the meteorites, which are the achondrites. So just adding them just for completeness might also be a good thing.
Yeah, I certainly agree. I'm only hesitant because this is already a rather complicated story, and
Yeah.
We're opening up more complications. But
yes,
that's reality. Is that this is a complicated mixture. To say that we're not sampling other things is probably not correct either. It's to say that what we're sampling is weighted towards these things.
good.
Alrighty, and then let's see, do we have any other questions from the chat? It looks like we have, Paul, do you have any questions? Or at least Mike's unmuted, so, do we have any other questions in the room?
I guess because even with the iron meteorites and stuff, I'm assuming much more difficult to get, say, an oxygen isotope out of them. So is iron isotopes a possibility, or are there any types of metal isotopes that you could look at for potentially metallic based meteorites?
Certainly, and I would say that probably your best bet is looking at those nucleosynthetic isotope compositions. Probably the best way to do it. But I guess the reality is that a lot of these proxies have complications, whether it be the materials evaporating, covering up what the impact looks like, or the materials experiencing neutron capture processes. This is the most simple story we can do yet. I welcome other proxies, other things here. But I'm uncertain how they would look in terms of iron meteorites too. The same story applies where there's a lot of ungrouped iron meteorites that have weird compositions, and it's difficult to get to a solution that is encompassing how much diversity is present there, and it's being honest with the complications of how messed up the material is. Again, what we're seeing is the culmination of tens, hundreds of thousands of impact events, not just one. Just being mixed together. This is what is the mass spectrum being weighted towards, but there's a lot of stuff happening here. So other systems might just add a lot more noise present in the system. Mm-hmm. But yeah, these are all great ideas.
Alrighty. Say we can do, one more big question.
If you could take one more.
Yeah, we got like 6 minutes until 12. So if anyone has any other questions, feel free to ask them in the chat or unmute. And if not, I think that's it. Do you have anything?
Thank you very much, Tom.
You're welcome.
Right on, Tony.